Exercise number 21. Consider the following problem. Determine the maximum value of z, where z equals 2x divided by 3 minus y over 5, subject to 8.1x minus 4.9y greater than or equal to negative 10, 2x plus 1.9y greater than or equal to 6, and 65x minus 28y less than or equal to 52. A. Is this a linear programming problem? Explain the basis of your conclusion. Let's have a look. Determine the maximum value of z. Okay, this is an optimization question. So far we have one of the conditions met for being a linear programming problem, where z equals 2x divided by 3 minus y over 5. Okay, z is a function of two variables in this case, and what's important though is that the type of function is linear. Constant multiples of x, constant multiples of y. Alright, so it's a linear function. Let's look at this domain. All these inequalities here are constraints for x, y, and if we notice, each inequality is linear. And the constraint type is one of the three permissible, which would be one of greater than or equal to, less than or equal to, or equal to. It's always the case in here. Okay, this is indeed a linear programming problem because of all these conditions we have seen satisfied. So let's record that. Okay, so here we are. So yes, this is a linear programming problem. It concerns the optimization of a linear function, and the domain is defined by a system of linear constraints, each of which is one of the three permissible types: less than or equal to, or greater than or equal to. Alright, let's go to part B. If this is a linear programming problem, yes, then solve it with the assistance from the TI Nspire CX. Round all final numbers to 3 significant digits. Okay, what's involved for solving the linear programming problem? Well, we need to first take a look at the domain or feasible region of this function to see what's going on. Alright, now to have the calculator assist us, we really need to have the inequality in the form of y isolated on one side. So let's go ahead and start work on that. To help organize ourselves, we could reference these. Let's call this inequality 1. This could be inequality 2. We call this inequality 3. Okay, and our first step here was going to be to rewrite the inequalities. Okay, inequality 1, what to do here? Let's start off by subtracting 8.1x from both sides. Or you know what, here's what else we could do. A lot of decimal numbers, and we could actually purge those decimals by multiplying both sides by 10. Maybe we'd imagine doing that. So now it's 81x minus 49y greater than or equal to negative 100. Alright, then the next thing to do would be to subtract 81x from both sides. Alright, so we've sort of did 2 steps mentally here. Let's keep track of where we're at. We now have negative 49y greater than or equal to negative 81x minus 100. Okay, now how about dividing both sides by negative 49? It's an inequality, so if we divide both sides by a negative constant, we must reverse the inequality. Alright, this will leave us with y less than or equal to. And I'll distribute the negative sign so that it's positive 81x plus 100 divided by 49. We've sort of taken the negative of the 49 and distributed it through the negative 81x minus 100 to create this. And again, the inequality sign is reversed. Okay, let's go to inequality 2. This one, also a number of decimal numbers, which could be purged with an easy multiply both sides by 10. Okay, let's start off by doing that. So we are already making this look like 28x plus 19y greater than or equal to 60. Okay. Well, to solve for y, we could subtract 28x from both sides and divide both sides by a positive 19. That would leave us with y greater than or equal to 60 minus 28x divided by 19. Okay, let's go on to inequality number 3. Get this solved for y. Let's see. Maybe we first subtract 65x from both sides, leaving us with negative 28y less than or equal to 52 minus 65x. Okay, now we could divide both sides by negative 28. Now, if we're going to divide both sides of an inequality by a negative constant, we have to remember to reverse the inequality as well. Okay, so this will give us y, not less than or equal to now, reverse it, greater than or equal to. And I'll take care of the negative 1 by distributing it through this side first. That would mean 65x minus 52, and then divide by 28. Okay, looks like we've got our inequalities all rewritten, and at this point we are ready to proceed to the calculator. Okay, here we are at the TI Nspire, and to get started, I suppose we could decide to add a graph. Okay, now remember, in this problem statement, it does say that we are to be rounding all final numbers to 3 significant digits. Since that's the case, I want to make sure that our graph is keeping 5 significant digits, because these are going to serve as intermediate numbers from which we calculate the minimum or maximum z. So I need them to be extra accurate, otherwise I'll have intermediate rounding error. Okay, so how to get this resolved? Let's go to the home screen and click on Settings, and let's go to Settings and the Graph and Geometry settings. Right now this is set on floating decimal 3. We want to go to floating decimal 5. Okay, on that. Now we're pretty much set there. And while we're at it, let's make sure that our other settings are keeping at least 5 decimal places as well. Floating 6. Okay, more than enough. I'll just keep it like that. That's fine. As long as it's at least 2 more than what we require for our final answer rounding. Okay, having that in order, let's go back to our current document. Now, in this formula bar, we're going to enter the first inequality here. Alright, since it's an inequality, we first need to go back and delete that equal sign and replace it with inequality number 1 is a less than or equal to number 1. Notice it changes to a y less than or equal to instead of using f of x, because technically this is a relation, not a function, so we don't want to use function f of x notation in this situation. Nevertheless, let's proceed. It's y less than or equal to, okay, we have here the parenthesis, 81x plus 100 parenthesis divided by 49. Enter. Okay. Also, I'd like to see the formulation appear here, so I'll put the label on. Okay, I got that there. Let's see, maybe I'll move this label over here for now. May decide to move it again later, but anyway, there's our first inequality graph. Now let's go on to the second one, which means we need to hit tab to bring up the formula bar again, and once again we're going to back up to delete that equal sign, and in inequality number 2 it is greater than or equal to, Okay, and the rest of the inequality says it's y greater than or equal to parenthesis 60 minus 28x parenthesis all divided by 19. Enter. Okay. Now that we see this, we might decide a couple things. One is this label maybe is actually better off down here where it's kind of out of the way of things. Secondly, how about the graph, the label of the equation inequality for this green? Let's get that available. And perhaps we could move this up here where it seems to be out of the way. Okay, and kind of keeping track of things here. So far, the intersection is all in here, this very dark olive green region. Okay, so let's get our third inequality graphed here to complete our system. And that means we need to hit Tab, bring up the formula bar, delete that equal sign because in number 3 it is a greater than or equal to. And it is a parenthesis 65x minus 52 parenthesis all that divided by 28 and enter. Okay, now instead of this whole like angular region with this other inequality here, looks like it's been restricted to everything in here. Okay, this looks like it's probably going to be a triangular region. We need to see a little more graph. Let's do this. Let's select and pull this down. Okay, yeah, it does seem to indeed be triangular. Okay, let's see. We would like to have the inequality that goes with this graph available. Let's right-click and then have the label appear. Let's see, this blue one I suppose looks nicest about there. And now that we've moved things around, the green there, that's a good place for it. And the red maybe up there. Okay, now right now we see that this is the domain or feasible region, but it's not really that clear. I like to really make this much more clear. And to do that, I think I will, well, first let's get the vertices because we know those are very important to this. Okay, so let's go get the vertices of this region. What to do? We could go to the menu and pick up the points and lines and intersection points. By the way, when you see a little thing like this in the corner, that shows you have a tool operating. It's the point intersection tool. And if you forget what to do, you can just go over and click on it, and it'll tell you what to do. So you have to click on the first graph, then the second graph, and then you'll get your point of intersection. Okay. Anyway, let's go to this red one and click. And how about the blue one? And click. And there we can push enter to get our first point of intersection. Okay, how about this graph? And already the point of intersection of the green and blue boundary lines appears. I'll hit enter to make sure that stays there for right now. And this graph, and there's a third intersection point. I will push enter to make sure that stays there. Okay, now I want to start moving things around a little bit, and which means let me escape this process and then escape to put away the intersection tool. And now I'll start, say, grabbing this intersection point and putting it right to the, just to the left of its actual point. And let's see, this, let's move it so that it's not on top of that inequality there. That looks pretty good. This one, okay, let's see. I think I'll move this label down a bit and then grab this and move it over to, say, there. That looks pretty good. Maybe it would be a little better if I just moved the entire graph over like that. Now let's see, maybe there, and then move this way to the right like that. Okay, and this label could go up here maybe now, and let me move this up a little higher. This looks pretty good now. Okay, so we have these labeled inequalities. We have these vertices labeled, but we want to still make this feasible region very clear from the graph. Right now it's still a little hard to see. Here's what we can do. I will construct a polygon with rather a triangle with these 3 points in it. So that's a matter of going to a menu, and we can go to shapes and pick out triangle. Okay, now I'm going to wait until I see the the hand points out to the fact that we are right on this very specific point. So this is a good place to click to lock in one of our triangle vertices. Move over here, there's the hand, click, another vertex is locked in for part of the triangle, and then come up here, there, click again. Okay, now we have the triangle in place. We could go escape to have the triangle tool put away. Now let's grab this triangle for a minute, right click, and do some coloring. Okay, first the line color, how about bright red? Okay, that's in place, and then we can right click again and now get the fill color to also be red. Okay, great. Now let's eliminate all the other colorations on this screen here. We can do that by changing each inequality and just make it an equals, because we only need the boundary lines right now. We don't need to see all these various inequalities. Just need the boundary line to really be defining our region here. It's already graphed in red, so I'll go ahead and do that. That means it's a matter of going back to the entry line and expanding it. Okay, right here. Back up and make it an equal sign. Also, for some reason, this always leaves behind a little extra multiplication dot, which has to be deleted. So go to the right and delete that, and then enter. Okay, so now we've got that one turned into just an equal sign. Let's go back and work on this one here. Change that to an equal sign and delete that little extra multiplier. Enter. Okay, getting there. One more. Entry line. Expand it. This one. Right there. Backspace. 3 for equal sign. Get rid of that little multiplication dot and enter. There. Okay. Now, what's very clear from our graph is the feasible region. Only thing missing is perhaps labeling it as the feasible region. So time for a little bit of texting. I think I'll right click and click on text, and right here let's put in feasible region, and we can move this right next to it. Will be pretty good there. Okay, so at this point, this looks like a pretty nice graph of the feasible region. What I want to do is check this, make sure this feasible region is correct, because if this is wrong, everything else is wrong to follow this. Okay, so what I want to do is find a point that's clearly in this feasible region drawn and see if it in fact satisfies all of the original inequalities. And since I'm going to do this rather quickly, I want to pick a point with easy coordinates here. And here's just something you can do with this calculator in case you wanted to have clearly visible simple coordinates. You can turn on the grid, and that's a matter of, let's see here, going to the menu, the view, and show grid. Now we see points where all the coordinates are integers, like the point 1, 1, point 2, 1, 3, 1. They all have nice little points. So now I can look, I can say, okay, look at this point right where the hand is about to grip. That point is clearly in our feasible region, and that point is 1, 2. That'll be easy to work with. So let's take the idea that 1, 2 is in our feasible region. Let's make sure that it really does belong in the feasible region. Okay, so we're here. Check. Feasible region graph. And what we've done is we've said, okay, the point 1, 2 is in feasible region. So now we will substitute into each original inequality. Okay, let's take inequality 1. Now we can almost do this in our heads, so that's why we have this nice easy point 1, 2. Okay, looking at inequality 1, x is 1, y is 2. That gives us 8.1 minus, okay, 2 times 4.9, 9.8. How about that being greater than or equal to negative 10? Okay, well here is, what, negative 1.7, greater than negative 10? True. Okay, let's go to any original inequality 2. Here it is here. X is 1, so that's 2.8 times 1 plus 1.9 times 2. Okay, that would be plus 3.8. Is that greater than or equal to 6? Okay, let's see what is over here. 3.8. 4, 5, 6.6 is the left-hand side. Ah, true. Okay, inequality 3. We have 65x minus 28 by 2, 56. Is that less than or equal to 52? Okay, this is like 9 here. Certainly less than 52. True. Okay, so you know what? Looks like that feasible region is probably pretty correct. This check is not infallible, but at least it uncovers most of the mistakes you might make in shading the wrong side of the region, or if we made some algebraic slip up in not reversing an inequality sign, or all these kind of things. It very likely shows up in a very simple check such as what we've seen here. Okay, we're ready to proceed. Now that we have this feasible region here, very nicely graphed, we need to proceed to look at the vertices, and we know from a theorem of linear programming that now that we see the feasible region is non-empty and bounded, that Z will indeed have a maximum value and a minimum value, and each of these will occur at a vertex. Okay, so now it's just a matter of computing the Z value at each of these 3 vertices and selecting the maximum in our case here. Alright, so let's see how to do this in a nice accurate way. Well, we could, let's see, start with, how about this vertex? Click once and then twice. Now I'm able to copy this number. So that's a matter of Control C, it's copied. I want to get a spreadsheet going. So, Control, Add Page, and it's a spreadsheet page. Okay, right there I want to paste that number there. Control V, there it is. And to help people read this table, maybe we take a moment, and although this is column A, which can be easy to reference, it's also maybe nice to us to give a more descriptive name for this column. We're putting the x-coordinate or vertices here, so maybe I could put x, let's say, underscore vertex, or just VERT. That would be enough to designate vertex. Okay, and while we're here, this column here could be the y-coordinates of the vertices. So I'll label this as y underscore. Remember, in labeling variables on this calculator, you can't use blanks, so that's why I need to use an underscore and VERT. Okay. And what will go in this third column, this will be our z, and I think just to keep this from being confused with it, maybe a future use of simple z, I think I'll call this z underscore. Okay. Now, let's go back and continue getting our vertice coordinates put into our table here. We need the y-coordinate for this one. So, back here, and right there, click once, click twice, it's ready to copy. Control C copies it, and go back here, and then Control V to put it in there. Okay, next vertex, back to the graph. And we could go here, 1, 2, it's ready to copy. I'll go Control C, and then back here, there, Control V. Alright, get the y-coordinate, back here, 1, 2, ready to copy, Control C, back to the table, and Control V. Alright, third vertex, the x-coordinate. Here it is. Whoops. 1, 2, ready to copy, Control C. And to the table, Control V. The y-coordinate, back to it. There it is, 1, 2, ready to Control copy, and back to the table, Control V. Okay, it's in there. We have the vertex coordinates all in our spreadsheet. It's now time to compute the value of z at each vertex. To do that, we can come over here to the z column, and this is the title bar. Here, a formula bar. Okay, now we can make z equal to, well, let's look back at the original formulation, and it says z equals 2x divided by 3 minus y divided by 5. Now for this spreadsheet, we have two choices to refer to x. One is to use the a here, or the other choice is to use the x vert. Alright, since a is simpler, I think I will use that in this formulation. So here we go. We're going to put 2 times a divided by 3, and then subtraction, and okay, there's y, so we'll use the b divided by 5. Okay, enter. Alright, here we are with our tabulated z's. Now the question is asking us for the maximum value of z. That looks right here, this 1.55. Okay, so ready now to write a conclusion about all this. And for that, perhaps we could go to there's a text application in this Nspire called Notes. So we could actually do something like this. Let's control. We can add a page and add some notes and start writing up a conclusionary statement. The maximum value of z is 1.55. Remember, now that we're in the conclusion stage, it's time to follow the instructions of the problem and round to 3 significant digits. Now, that actually is our responsibility of this question. I do like to make a complete conclusion even if I'm not asked to do so. And so where does this occur? Okay, let's go back to that spreadsheet and go get that information. Okay, so this occurs at the point xy equal to 5.83 Again, we need to round this to 3 significant digits now, and the y-coordinate rounds to 11.7. Okay, so let's write that down. This occurs at x, y equal to 5.83, 11.7. Okay, now we could go ahead and capture these pages as well, get them ready to put on our solution. Okay, right now the formula bar has the formulation for z in it, but you can't quite see it all, and we can fix that up by expanding the width of this column here. In fact, I don't even need a column D for this question. 3 columns is all that's needed, so maybe expand about like so, and then capture the image of this page at this point. Okay, so I've taken those document pages and printed them on the solution page here, so this pretty much completely finishes the Part B question. The last thing I like to do, though, is the conclusion statement here. I like it to be a little more prominent. So here, our big conclusion, the maximum value of z is 1.55. This occurs at xy equal 5.83, 11.7, and maybe put this in a nice prominent cloud to finish up. Okay, great. Part C. Using calculator and or computer apps, illustrate this problem graphically. Okay, now this question means the big picture. Z is a function of 2 variables, so the big picture graph of the situation is a 3D graph. Okay, when you have z, a function of 2 variables, you got to go 3 dimensions to get that graphed. Thus far, the only graphing we've been doing has just been the domain. That feasible region, that's just graphing the domain. Those are the allowable xy's, and that's just in the plane. Okay, so let's return to the Nspire and open up a new page and go work on the basic 3-dimensional graph, and then we'll have to add the additional details by using Microsoft Paint to get our finished product. Okay, add page, and let's see, this time we have in mind adding a graph, and let's go to the menu and view and 3D graphing. Okay, now looking back at the original formulation of z here, we can put it right in here. So we have 2x divided by 3, so I'll say 2 times x divided by 3, and then minus y over 5, subtraction y divided by 5, and enter. Okay, we expect to see a plane in 3 space for a function z, a function of x and y, linear, and that's what we have going on here. I think I would also like to first hide that box. So under the viewing, I picked the option of hiding the box, and let's let me take a little look at this. Let's have it revolve around, confirm that it really is a plane, and that's surely the case. Now another question is, how about selecting the range on each of the axes here? If we kind of look back at our feasible region lied entirely in the first quadrant, and it had let's see, x is going well, we'll say from about 0 out to as much as about 6, while the y-coordinate had to have about 0 to 12 to expose the feasible region there. Okay, I suppose in this case, to keep each axis scaled the same length, I'll go with that 12 units menu, and the range zoom, the range settings. Okay, X min, we can say 0, tab down. We'll go to 12 and then tab down, scale it at 1 apiece on the axis, and the Y we decided is 0 up to 12 and 1 apiece. And for Z, let's see if we have, what if we had -6 to +6? See if that works out fairly well for ourselves. We can make any other decisions after we see the result of this. Okay, let's see here. Okay, this looks like it's going to be pretty good for our purposes here. Let's see, I'm picking an orientation that might be best for our graph. Z. Okay, back to this range zoom, and let's okay, Z min -2, Z max 10. Okay, let's go with that. Now, okay, this should look pretty nice. I think that view will be giving us a really sharp looking graph. We now need to take this to another application to sketch in the feasible region and project onto the surface to show the actual graph and identify graphically where the maximum point seems to be. Hopefully it'll be consistent with the algebra that we've done thus far. Okay, so let's take a screen capture of this. And actually, sometimes I actually prefer the view to be the computer view for these pictures. It seems like it comes out a little bit better resolution. And now go to the camera, capture this, and I'll take this image to Microsoft Paint to do further work. Okay, after we apply the other graphic features to the TI Nspire 3D graph of that overall plane, we have the following. The feasible region, the allowable XYs, are here in the blue, and there's that triangular region there. Now, as it turns out, this red plane actually passes through the XY plane, and you can resolve that equation by actually setting z equal to 0 here, and you can confirm yourself. You end up with a y equals 10/3 x, which is here in this red dashed line. Now, we take our feasible region and we project it directly onto the red plane to find the actual graph of the function, which is in the green here. It's a planar triangular surface in 3 space, and what we were looking for, the maximum z, so that's like the highest point on the z coordinate of the highest point on this green surface, right about there. And we said that the maximum value of z occurs when z is 1.55. This occurs when xy equals 5.83, 11.7. You may notice our green surface graph actually dives a little bit below the xy plane at one point, which explains that one of those vertices had a negative value for its z as well. So everything seems to fall in place here for consistency. And again, trying to appreciate the overall graphic picture of what's going on in this problem is really nice and available to us with the 3D graphics that are coming along in the technology area. Okay. Exercise number 20. Consider the following problem. Determine the minimum value of z, where z equals x cubed over 3 plus y cubed over 3 minus 5x squared minus 3y squared plus 23x plus 2y, subject to x is greater than or equal to -10 and less than or equal to 5, and y is greater than or equal to -10 and less than or equal to 5. Part A. Is this a linear programming problem? Explain the basis of your conclusion. Alright, well it is. an optimization question because we are determining the minimum value of z. However, look at that function formulation. Z equals to an x cubed over 3. Okay, right away, this is not a linear function. In fact, it has, let's see, there's an x cubed term, a y cubed term, a negative 5x squared term, a negative 3x squared term. There are 4 violations of being linear in that formulation right there. So that's the end of the story as far as this problem being linear programming. It isn't, and it's because the objective function there is not a linear function. Okay, let's record that. Okay, so there we are. No, this is not a linear programming problem. The reason is that the objective function is a nonlinear function. Part P. If this is a linear programming problem, solve it with assistance from the TI Nspire CX. Okay, stop right there. It's not a linear programming problem, so this is not applicable. Make a note of that. Okay, Part C. If this is not a linear programming problem, solve a graphic approximation with assistance from the TI Nspire CX. Record all final numbers to 2 significant digits or the nearest tenth. Okay, let's get started with that. Okay, as we see, we have z, a function of x and y. This means we need to have a 3D graph. Okay, so let's open up a graph page, and let's go to the menu and view a 3D graph. And let's write in the formulation here in this entry box. Looks like we have an x caret cubed, forward arrow to get out of the exponentiation box. Then we got to divide by 3, and then it's plus a y cubed, y caret 3, forward arrow to get out of the exponentiation box, divided by 3, then subtraction, 5x squared, subtraction, 3y squared, plus 23x, plus 2y. Okay, a little proofreading. It looks like it's been transposed properly. Alright, now I suppose we notice the domain of this function is very simple. With x lying between 2 specific numbers and y lying between 2 specific numbers, this will be a rectangle in the xy plane. And we can actually get this domain to be our xy plane just by setting the ranges of the axes. So this part is pretty easy to set up. Let's go to the menu, range zoom, range settings. Okay, x min, there's our negative 10, tab forward, up to 5, which is actually the default range max, so tab forward, scaling, okay, 1 apiece perhaps. The y min, okay, negative 10, tab forward, and 5, the default is already there. Y scaling, let's say 1 apiece. Now, beyond that, we don't really know too much at all about the z-axis right now. The only thing that would be nice, perhaps, to be to make the z-axis the same length as the other 2 axes, which are 15 units long. So perhaps negative 10 here for z-min, and z-max is already 5. There was our 15 unit long z-axis. Maybe scale it 1 apiece. Click OK there, and let's hit enter here since we have our formulation in order. Okay, we have this situation here. Let's see what we think. Okay, looks like this function is well, there's just a little bit of it here, and it's very steep. So we're expecting that there must be some very large values of z here, and they're not going to appear if we only have a z-axis going from negative 10 to 5. You might think it'd be a good idea to just make a really long z-axis. But that's not a good idea, because the best graphs on this particular calculator happen to be the ones where all the axes are scaled the same length, or have the same length to begin with. Let me show you what I mean by this. So let's say we decide to let's just make the z-axis from negative 100 to positive 100, thinking that we'll get a lot of graph to appear. So we go here to this range, and we go to the range settings, and we go back down here to where we had our z-min, z-max settings, and we say, okay, look, let's just go negative 100 there, and let's go positive 100 here, and we say, okay, and you get something like this, which is pretty much impossible to do much with, not very visible. Okay, so cancel that idea. Let's perhaps just go back and change those z coordinates back to what they originally were for a moment, to think of a new strategy we could use here. Okay, so we had a z-min of negative 10, a z-max of 5. Now it's 15 units long. Okay, let's see, what could we do here? Let's see. Another strategy could be this. Instead of using our formula for z just the way it is, we could divide z by, say, 10 or even 100 or even 1,000, which effectively shrinks the z-coordinates all towards the xy plane. Alright, so maybe we can try something like that. Here's what I mean. Let's bring back the formula. Okay, now I need to put a couple parentheses around everything. So parenthesis there. And let's go out to the end here. Okay, after the 2y, another parenthesis there. Now, let's divide this by, and I like to choose powers of 10. This function looks rather really steep with some large z values, so maybe I'll divide it by 100, and maybe it takes 1,000 or 10,000 to make this work. But let's start off right now with divide by 100. Hit the enter here. Okay, now actually this looks a lot better. We actually seem to have, let's look underneath. Okay, now we have gotten almost the entire graph to appear on this coordinate system here. The only little trouble is we're missing some graph right in here. Alright, two possible solutions. One, we could divide z by an even larger number to further shrink it towards the xy plane. Or since we're not really missing too much here, maybe I will just try expanding the z-axis a little bit, not a lot. Remember, the axes are best identical lengths. A little bit of difference between them is not too bad, so let's try that. It looks like we need a little more negative z-axis, so I'll go back to the menu. I'll go back to the range here, back to the range setting, come down here to the z-min. A little more than this. Maybe let me try negative 15. Okay. Okay. We're just missing a little bit. That wasn't quite enough. Okay. Let me just go back and go negative 20. That will for sure do it. Okay, yeah, now we for sure have got the complete graph in sight. Now I'm getting ready to kind of take a picture of all this. A few things I tend to like to do. This box I want to actually not have in sight right now. And there's a couple reasons for that. One is I think the regular graph looks better without it actually at first. So let's hide the box. Okay, now I got this. Now I want to get a nice angle on this for viewing. Okay, perhaps about there. Let's see if I can zoom in a little bit here with that. Okay, pretty good. Now I will capture this image here. This is the overall picture, so I capture that image. Now what I need to do to go along with this is I also need to have images of the ranges of the axes, the window, and I also need to know what function I have here, because here's what I want to do. I actually want to label this with the function, the original function formula. But how can I do that? This is actually the function z equals to the formula divided by 100. Okay, what I'll do is, instead of labeling the axis, the z-axis with the number 1 there or so, I just multiply those axis numbers by 100 instead. So now the z-axis, which presently goes from -20 to 5, we will label as going from, let's see, -2000 to 500. And that way we have the original function being graphed with the original formulation. So that's how you can take care of getting a function to appear on your graph and being able to properly label your axes. The trick is divide z by some nice convenient power of 10, or it could be any number, but powers of 10 are most convenient, I suppose. And then you actually just take it, you actually compensate by scaling the axes accordingly to make up for how you have shrunken the graph. Okay, so the other things we need: the formula for z. Okay, I want an image of this so I don't forget what was done to get this graph to appear. And then the other thing is to pick up the window settings, range settings. Okay, here's the x-axis and y-axis. Capture this image. And then I'll need to go down here and get the z-axis information. Okay, and capture that image as well. Okay, that's in order. Okay, so now we've got a nice picture of the overall graph. Now this question is concerned with finding the maximum value. Okay. Well, from here it's kind of hard to see just what is going on there. There's some maximum, looks like it's in the first quadrant, but the graph really kind of levels off when we are looking at that first quadrant. Let's see, what could we do here? Well, a couple things. That strategy we used when we divided z by 100 to make it appear, now we probably need to change strategies to expand this graph away from the xy plane so that it shows a greater degree of change and the maximum point will be more evident. Okay, so here's what we can do. What is z right now, for instance, at a maximum? It's hard to see much of anything there. The z-axis right now goes from 1 to 5, and the graph just kind of comes up here a little bit above the xy plane. It's hard to see too much what's going on. Alright, here's what we might do. We can change the formula of z to only divide by 10. That will raise the points, the z coordinates, all by a factor of 10. And then we can also decide that the first quadrant seems to have the maximum point, just kind of the way it looks here. So maybe we'll set up our x and y axes to only go in the first quadrant, and then the z only, let's see, multiply that by 10. We'll make the z-axis a little bit big. Maybe z goes from 0 to 50. Okay, let's try that. So back here, range settings. Okay, we were thinking the maximum looks like first quadrant. Alright, so 0 and 5 for x. Okay, and 0 for x min, 5. Okay, now although we do kind of want the axes to be the same, just for this intermediate searching, a z min of, let's say, 0, and a z max of, well, 50. Okay, if it's too big to even see what's going on, we can change it, but let's just start there for now. Change the formulation so that it is just divide by 10 rather than divide by that 100. So back here, make the z-coordinates 10 times larger by only dividing by 10, and hit enter. Okay, now we start to see something that's, well, a little visible, but still looks like we don't need nearly this much z-axis. Alright, maybe we make z just go from 0 to 20 perhaps. Okay, back here, 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 and maybe z max, in fact maybe only 10. Okay. Alright, this is starting to look a lot more visible. Let's see. A maximum point here. Alright, just from this angle, looks like when x is, right now x goes from 0 to 5. So x around 3-ish looks like that's what x is going to be, approximately. On the y, it looks y is not too, maybe around the vicinity of 1 or so. Okay, and so let's keep track of that. 3, 1, and the z here, let's see, z right now goes from 0 to 10, and so maybe about 4 is what we need to center z around. Okay, so remember those numbers here. We said it was for x around 3, for y around 1, and for z about 4. Okay, so 3, 1, 4. Let's go back to the range. Now I'm going to center things around 3 for x, so I'll make it go from 2 to 4. I'm going to change the scaling to 0.1 per unit right now. The y-axis, we're thinking around 1-ish, so I'll make it go from 0 to 2. On the z-axis, it looks like just going from 3 to 5, perhaps. Centers that 4 in there. Okay, we try all that. Now we have this. Okay, let's see here. What about this? It looks like we have a maximum. Let's put the box back on and see what's going on here. The box is actually now handy because we want to see some kind of coordinates here. So let's show this box. Okay. Now with this, we get a better idea what's going on. Okay. Now z is right now between 3 and 5, and it looks like about 3.3 or so, based on what we see here. 3.4, 3.3, something like that is about a maximum of z. Keep in mind, we have still got the function divided by 10. To get ourselves to get now even a better look at the kind of behavior of z here, the full maximum type behavior, maybe it's actually now a good time to go ahead and let z be its original function, which will multiply these z-coordinates by 10 if we change it back to original z, and then we'll just make up for that by making z be in the vicinity of 33 or 34. Okay, so let's try both of those ideas. Go into the menu, going to the range settings, making z. Okay, now let's say we'll say 30, just for starters. Maybe we go 32, and perhaps up to 35. That might be a conservative starting point. Okay, there. Now we need to go back to our function formulation and make it the original z. So now no longer even divide by 10. Let's say goodbye to all that. Now we actually have the actual z function. Hit enter. Okay. Okay, okay, now this looks pretty good. Here we see a real clear maximum point appearing on our graph finally, and the only thing we might do, maybe we bring things in a little closer. Let's take a look at the coordinates that we think we expect here. Now that I look at this x right here, here's 2, here's 4, that makes this 3. It looks like about 3.5 or so for x. Now the y, here's 0, here's 2, there's 1. Okay, looks like about 0.5 for y. Okay, so we got 3.5, 0.5, and the z, there's 32, there's 35. This is scaled at 1 apiece, I believe. 32, 3, 4, yes, 1 apiece. So the maximum z actually looks very close to 34 here. Alright, let's go back and even create a zoomed in version of what we have now. Back to that range settings. Okay, we were thinking 3.5-ish for the x. Let's say 0.3 to each side of our little estimate there. So we'll say 3.2 tab and 3.8 tab, 0.1 apiece. The y, okay, near to 0.5, so we'll say down to 0.2 and 0.8. Scaling at 0.1 per tick mark from now on. The z looked rather close to like 34ish or so, so we could say, for this maybe not quite such a tight range, we'll say maybe 33 and 35. Okay, that's pretty good. Maybe we keep it like so. Okay, let's see what we get. Okay. You know what? Maybe we make the z-axis not quite so long. We don't need to go up to 35 apparently. Looks like 34 will about do it. In fact, we could start at probably 33.5 and go to 34. Let's try that. Okay, 33.5 and just 34 might do it. Let's try that. This way all the axes are very close to being the same. Okay, this looks really nice. Now how are we going to locate this point even better than the kind of visual we've been doing so far? Well, there's this nice trace feature. Here in the menu, tracing, a z-trace. This will bring up a horizontal plane slicing through our graph. And we can move this horizontal plane. We want to be just tangential to this surface. So maybe we sight down from the top down, and to move this plane, you can go Shift, arrow up, Shift, arrow up. Okay, yeah, we're getting higher and higher. Now I need to make sure that we have there. Okay, we're starting to see that we have a plane all the way around, which I want to make sure we didn't miss the maximum point here. It's here. Now we can just get closer and closer. Let's see how much the z changes when I push shift here. Right now it's at 33.875. If we go up, it goes 33.9. Okay, it's changing rather small increments. Oh, but look, now we've overshot. Okay, if we go back, it's about there. It'd be maybe nice if this plane would not move so much with each click, right? And you can change that too. What you can do is go to the menu, tracing, the trace setup. Okay, now here in this number of z trace steps. This is how many clicks it's going to take to traverse your entire z-axis, whatever you have set. Right now it's set at 20. Well, if we divided that into that z-axis into even more steps, that would make the plane move less rapidly, and maybe we could go to maybe we'll try 100. Really kind of aggressive, and go with that. All right, now let's try shifting up again. So we can go and shift up, 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 up. I'm using my computer keyboard now because it's a little easier for me to just hold the shift key down and keep continuously hitting the up arrow. Okay, smaller, smaller, smaller. Oh, this is, oh, okay, that's too much there. Go down one. Okay, from here, I think we can get everything we need. Now notice, okay, look at that Z there. It's 33.9 approximately. If we go down a level, it's still 33.9. If we come up one, it's 33.9 itself. So this is ever so slightly less than 33.9. Okay, so we have a very good Z coordinate. Now, let's see, what do we want to say about the Y coordinate right here? Maybe, let's see, maybe this is a good view? Or maybe a little more, maybe underneath. You can try different ideas depending on whatever is going to be the best for you. Alright, looks like 0.4 for Y. Our directions ask us to get it to either two significant digits or the nearest tenth. Okay, it's pretty clearly 0.4. That locks in our Y to the required accuracy. Let's now look at the X coordinate here. Kind of size this up. Our X-axis, maybe right about this view is probably going to give us the best X. Right now we have a 3.2 here. Here's 3.5. That can be, okay, no, I'm sorry, that's 3.8. Okay, and these are tick marks at 1/10 per tick mark. So 3.2, 3.3, 4, 5. Right, it looks like kind of in between these two numbers here, so maybe we say 3.55 for X. Okay, so there's our approximation of this maximum point, 3.55 for X, and the 0.4 for Y, and the Z about 33.9. Now I would like to take a picture of this image to go with the solution. In this case, I'll keep the box. Try to get a kind of a nice angle here. I'd like to get the x-axis maybe in its normal position. Okay, kind of going off to the right. There's the y-axis. And let's see. There, that looks pretty good right there. Here's a good image to capture. So we should capture this highly zoomed in graph, and so that we make sure we don't forget what else is going on here, we also want to capture the present formula for Z we have. Tab up here. There it is. Capture this. It's the original Z we're working off of right here. Okay. And then let's go ahead and also get our range settings. Although it's pretty clear from that graph, in case we forget what happened here, it's not a bad idea to capture these as well. And the Z range. Okay. Now we can take these images, and go to Microsoft Paint and sketch up our final graphs. Okay, and here's the final product. In the upper left is the graph of the original function. Notice the z-axis has got scaling marks from -2000 to 400. Remember how that came from. We actually sketched the graph of a z divided by 100, but then we make up for that by scaling the axis, or changing the axis tick marks to be multiplied by 100. This way we get the actual original function to appear on our graph. Secondly, we did a lot of zooming in to eventually arrive at our maximum point prediction of this graph, and we used the assistance of that tracing horizontal plane to slice through our graph until we saw ourselves being just about tangential to the graph. And there's our final answer, where our maximum value of z is approximately 33.9. We also point out where it occurs because we make the statement that the maximum point on the graph is approximately 3.6, 0.4, 33.9. Also, by methods of calculus 3, which is not the intent of this exercise, it can be also confirmed with consistency that this approximation is indeed accurate to all of its decimal places and digits shown. Okay, very good.